In this model, we will simulate RF heating of a waveguide bend containing a dielectric block. A guided wave enters the assembly on one side and propagates throughout the waveguide structure, interacting with the walls and dielectric block. The waveguide will experience electromagnetic losses in the block and waveguide walls, which will induce a temperature rise in the assembly, leading to thermal expansion. Our results will calculate the magnitude of electric field, rise in temperature, S parameters, and power dissipation. Let's start the model by opening Comsol Multiphysics and using the Model Wizard. We're going to be building a 3D model, and under Heat Transfer, we select Electromagnetic Heating and choose the Microwave Heating interface. You'll notice here that 3 physics nodes were created for us when we added microwave heating to our model: electromagnetic waves frequency domain, heat transfer in solids, and the multiphysics node, which couples the first two. The microwave heating interface will solve for the electromagnetic waves and temperature fields of our assembly. Moving on to the study, we're going to solve this model using a frequency transient study type. Click the Done button, and we are brought to the Comsol desktop. Let's begin by adding parameters, our geometry, and some selections to use later on in this model. So, in the Home tab, click Parameters, and enter the following settings into the table. F0 will be the operating frequency. LDA0 is the air wavelength, and Hmax is the maximum mesh element size for air. Note that cconst is a predefined Comsol multiphysics constant for the speed of light in vacuum. Next, import the model geometry. In the Home tab, click Import and browse to where the rfheating.mph bin file is stored on your computer. This should be located in your Comsol folder under Models, RF Module, and then Microwave Heating. Select the file, click Import, and the geometry will appear in your graphics window. Create explicit selections to ease the process of defining the physics later on. I've skipped over this to save time. Click the wireframe rendering button to view the geometry better. The first explicit selection defines the structure of the waveguide. The second and third define the inner and outer surfaces of the waveguide, respectively. The fourth and fifth explicit selections define the air region within the waveguide and the dielectric block. Next, we move on to the physics. Go to the ribbon, and in the Physics tab, select the Electromagnetic Waves Frequency Domain interface. This is set to solve Maxwell's equations in all 3 domains. However, we will remove the waveguide from the selection since the skin depth of the waveguide is small relative to the dimensions of the waveguide, and the electric fields are essentially 0 in the interior of the waveguide. We want to consider the effects of finite losses due to the material conductivity of the waveguide walls and in the dielectric block. So, we will add an impedance boundary condition to the waveguide walls to account for the skin effect. From the selection list, choose Waveguide Inner Surfaces. The losses in the dielectric block are handled automatically by the governing equations. We'll also want to define 2 port boundary conditions to specify where electromagnetic energy enters and exits the waveguide structure. Click on Boundaries and choose Port. Select Boundary 15, designating it as the input port. In the Settings window, find the Port Properties section and change the port type to rectangular. Turn on wave excitation at this port and enter 500 watts for the port input power P-in. The TE10 mode is applied at this port boundary condition. From the ribbon, add a second port, and on the other end of the waveguide, select the corresponding boundary. Change the type of port to rectangular. This is the output port. Again, the TE10 mode is applied. Now, go to the ribbon and select the Heat Transfer in Solids interface. This is set to solve for the temperature fields in all three domains. Use the Select and Hide button to hide the top, outer, and inner surfaces of the waveguide to get a better view of the inside. We will assume that the air inside acts as an insulator, so we remove it from the selection. Go to the Physics tab, click the Boundaries button, and add a temperature boundary condition to the two ends of the waveguide. We'll assume that whatever structure the waveguide is bolted to is being held at a constant temperature of 20 degrees Celsius. Let's also apply a convective heat flux boundary condition on all of the exterior boundaries of the waveguide. This is going to approximate some small amount of free convective cooling to ambient air. Under the heat flux section, specify a heat transfer coefficient of 5. This is a typical textbook value. You'll see that the couplings for the two physics in our simulation are already defined in the multiphysics node. The electromagnetic heat source is going to take the dissipation as computed by the electromagnetic waves frequency domain interface and pass it into the heat transfer in solids interface. We also have a boundary electromagnetic heat source, which is applied to all boundaries by default. However, Comsol multiphysics automatically figures out the boundaries where it makes sense to apply this multiphysics coupling to, the waveguide walls. Next, let's specify the materials in our model. Go to the ribbon, and in the Home tab, click Add Material. Begin by specifying aluminum for the waveguide structure. Under the built-in tree, select aluminum and click Add to Component. In the Geometric Entity Selection section, under the selection list, you'll see the named explicit selections we created previously. So we select waveguide. Add air from the built-in tree and select the air domain. Assign the FR4 circuit board material to be the representative lossy dielectric material for the dielectric block. Last, we'll assign copper to the waveguide inner surfaces. This represents some high conductivity coating applied to reduce losses on the interior boundaries of the waveguide. Now we're ready to mesh the geometry. We want to customize the mesh for the air domain, so right-click Mesh 1 and choose Size. In the Settings window, under the Geometric Entity Level list, choose Domain and select the air domain. In the Element Size section, click the Custom button, check the Maximum Element Size checkbox, and enter Hmax. We'll also want a custom size setting for the dielectric block. In the Settings window, change the selection level to Domain and choose Dielectric from the selection list. In the Element Size section, click the Custom button and change the maximum element size to the following. Finally, we need to create a free tetrahedral mesh for the waveguide structure. Then we can build the mesh. Before we solve our frequency transient study of the assembly, we'll want to modify the study settings. In the Model Builder window, select Step 1 Frequency Transient. In the Settings window, click the Range button to add a range from 0 to 60 seconds with the output recorded every 10 seconds. Check the Relative Tolerance checkbox, and in the Edit field, type 0.001. The relative tolerance controls the time step size taken by the solver. In the Frequency field, type F0. In the ribbon, click the Compute button to run the simulation. Once the model has solved in Comsol multiphysics, the default plot of the magnitude of the electric field is shown. There's also a plot showing the temperature of the model, and we can see that the dielectric block heats up the most. Let's create a plot of the peak temperature over time. Go to the ribbon, and in the Results tab, click the More Derived Values button and select Volume Maximum. Apply it to the dielectric block. Click Replace Expression, and from the menu choose Heat Transfer in Solids Temperature, Temperature T. Change the units to degrees Celsius and click the Evaluate button. Next to the Messages tab, a table is generated containing the stored values at each time increment. Click the Table Graph button to automatically create a 1D plot group node with a table graph plot, and we can see how the dielectric block heats up for 1 minute of operation. We can also show the circuit characteristics of the two ports through S parameters. In the Results tab, click the Global Evaluation button. In the Settings window, click Replace Expression and select Electromagnetic Waves, Ports, S parameter 11 component. Click the Evaluate button. Again, a table is generated. Finally, we will create a plot of the power dissipation. Click the More Derived Values button and select Volume Integration. Select the dielectric block and replace the expression with electromagnetic waves, heating and losses, total power dissipation. Evaluate the expression. Our results show that we are dissipating about 7.7 watts, which is what causes the temperature rise over time. This concludes our building of the model. Learn more about this and similar models at comsol.com/models.